Okay, yeah, thank you so much for coming and then during the bad weather. So, as Michael said, I'm Yasuhiro Hasegawa from the JPA. And if you care about my kanji name, there's no
Pointer?
yeah, pointer.
No, there's no pointer.
Oh, no pointer, okay. Yeah, so then that's the kind of my Japanese name, which is there are so many strokes. Okay, so then today I like to talk about the planet formation stuff. So how to form the planet, and then what's the current status, and then how we like to go forward in the future. And then if you have any question, just ask me. Then I'm really glad to the young scientists or engineers here. I'm so excited about, and I'm gonna convince you guys to jump in this our thing. So, right, let's get started. Also, then, before just talking about the science, just a little bit about me. So then, actually, when I was a kid, I saw the Apollo 13. So have you guys seen the movies? I think this is so exciting, right? This is the so-called most successful failed mission. So then, as you guys know, Apollo 13 was failed because of some kind of issue on the spacecraft. But then the NASA engineer actually working hard to get the 3 astronauts back to life alive. So then I was so excited about it. And then when I was a kid, oh wow, it's really amazing. And I really like to work on NASA, so I did this kind of space science. But then, through the Japanese, kind of title education, I noticed that I think that maybe quantum physics is much more interesting. So that's why gradually I'm more interested in physics or quantum stuff when I was an undergrad. So that's why I decided to study the quantum physics rather than the space engineering. And then, as Mayuko said, after when I get the master or PhD, I decided to work on astrophysics. And then right now, I'm not a scientist at JPA. So then actually I'm really kind of slave of the physics, because if you think about the gravitational potential energy, then maybe the engineering is maybe the potential energy is so high. Then if you just do science, then maybe again potential energy is high. So then at JPA, actually the JPA is more like an interface between the science and the engineering. So that's why I'm at again the slave of the physics, and then now in the kind of really the minimum of energies. Okay, so then this is kind of about me. So then let me move to the science part. So then why we care about the planet formation, right? So then if you look at the night sky, which is really beautiful, then actually really during the ancient era, the people are wondering how many the planets out there, and then also is the solar system unique, and then are we alone? So this is really the kind of fundamental question of the human beings, and then the planet formation is one of the key scientific area to address this kind of question. So that's why that I think the planet formation is really critical to understand. Okay, so then what's the fundamental question of the planet formation, which is essentially we really care about where and when and how do planet form. So this is essentially the reason why we are working hard. And then actually I try to pretend of some kind of expert, right? But then actually this is a kind of quite unique question for anything. So then, for example, if you they say you are looking for the yummy fish and chips, right? So then and then you still know that this essential sentence. Yeah, okay, so then it works, right? And then you already here, so that's we already know where. So you have to be here to get a nice, fun, the yummy fish and chips, and then the when. Of course, we like to get really fresh food, right? So that's essentially you like to get the yummy fish and fish. It should be ordered now, and then you're gonna eat it immediately. And then for how. I think that if you're already here in Japan, so that's why that you already, I guess you guys understand Japanese cultures, but then actually we don't ask the chef how to make it. Right? Instead, we like to observe the chef and then try to do the shadowing, and then we like to speculate how to form the yummy fish and chips. So then so that's why this is the kind of again that kind of same for everything. And then but then here essentially we like to focus on the planet formation. So that's why let me jump into the one of the famous systems, which is the solar system. And then so then I guess you guys already know that all the planets, right? So then does anyone coming from the US originally? Oh, good, good, good. So then, what you think about the Pluto? Do you guys think? Are you guys think it's more like a planet or dwarf planet? Are you?
Well, I think it might be different for most Americans. I don't think it's a planet.
Oh, okay, I see. Good, good, good. But anyway, yeah, I think that right now, yeah, Pluto is now it's called a dwarf planet. So the main reason is that essentially the Pluto-sized planet is there are so many Pluto-sized planets, and then maybe Pluto might be one of the Kuiper belt object. But then I think the US people are so proud of it because this is the first planet discovered by American astronomers. But anyway, I think the Pluto also is we consider that's the kind of leftover of the planet-forming material. So that's why it contains really the important information. But anyway, based on that IAU, International Astronomical Units or something, then essentially now we have 8 planets in the system. Okay, so then actually the solar system is really interesting in the sense that all the planets in nearly the coplanar. So this means that the inclination, which is the kind of the height from the midplane, is relatively low. So that's why actually long time ago people already think that the planets are likely formed out of the flattened disk, like this. So then this is a kind of our initial hypothesis to how to form the planets. And then also if you look at the composition of the planets, then the inner one is more like a Rockies, right? And then actually the inner Earth, we of course have a waters, but then if you look at the mass fraction is really low. So that's why that we think that, and then if you look at say Jupiter or Saturn or Uranus, Neptune, then these guys have a so-called gas giants and then contain lots of the volatile. So then looks like that maybe that there are sharp transition in the composition in the disk. So that's why this is a kind of our initial the kind of starting point to formulate how to form the planets. All right. So then so this is a kind of a cartoon of how the protoplanetary disks, and then so that as I said, essentially we think that here is the central stars, and then central star has the magnetic field, and then essentially the magnetic field is the cross from the one coming from one surface and then ended on the other surface. So this is so-called dipole magnetic field, and then close to the central star, temperature is high. So that's why we think that that's composed of the gas mainly. And then if the temperature is lower than about 150, 100 K, then maybe that some kind of solid is emerged because temperature is low enough. And then, as I said, at about 150 K, it's a so-called the snow line. So then beyond the snow line, all the water is becoming an ice phase and then condensed to the ice, and then there are so many the solid there. And then and then this is just for the information. We think that the protoplanetary disk, which is the birthplace of the planet, the composition is about 90% of the gas, and then gas means that the hydrogen and helium. So that's why really the lightest elements. And then only the 1% we can say solid, which is heavier than the helium. And then so this is a kind of the astronomical world. So and then also the size. Of course, each disk has a different properties, but then roughly about 100 to 200, the size is 100 and 200 AUs, and then if you compare with the solar system, which is about 30 AU, so that's why maybe factor of 3 or maybe the factor of 7-ish larger in the protoplanetary disk, and then we think that this is a kind of birthplace of the planet. And then one of the interesting comparisons is that the protoplanetary disk, the density at the location of the 1 AU, which is the distance between the Sun and Earth, density is 10 to minus 9 gram per centimeter cubic. So but then if you look at the atmosphere of the Earth, which is 10 to 9, so that's why it's a huge difference. So then our atmosphere is so dense compared to the protoplanetary disk. So that the protoplanetary disk is so tenuous. But then we think that this is the kind of birthplace of the planets. And then the question is that, of course, this is kind of theoretical view and cartoons, and then the key thing is that how we're going to observe them, right? And the observation is really the method to verify our the hypothesis. So then so then if you look at the suns or stars, whatever, then essentially the y-axis is the brightness, and then the x-axis is the wavelengths. So then if you look at the kind of point source, we can see that then this kind of the linear slope like this. But then if you have a protoplanetary disk, then the disk is also heated by the stars, and then that re-emit the light from the central star. So that's why compared to the sun, we can see the kind of excess emission, which is called the infrared excess. So that's why by looking at the brightness distribution as a function of the wavelengths, then we can see the presence of the disk. And then this kind of structure is really useful in the sense that where the planet-forming material is distributed, right? So then for the bottom, I think there are gap. Then there are no material to re-emit the light coming from the central star. So that's why you can see some kind of the depth like this. And then once the disk emerges, then you can see that the infrared excess like this. So then so this is one of the way to observe to confirm the presence of the protoplanetary disk. And then actually this method is really good because we can essentially apply to that many star-forming regions. And then so this is a kind of the sky we can see, and then the mid-planes are kind of the Milky Ways. And then depending on the location, we can see that the various star-forming regions. And then these guys also called nearby stars, and the nearby means that about 500 light years away from us. And then maybe Taurus is there, it's also a famous one, then the Ophiuchus is there. And then the key thing is that if you look at the different star-forming region, ages are different. So that's why by looking at a different region, we can really trace the kind of evolution history of the protoplanetary disk. And then so this is the one of the outcomes. So then the x-axis is a kind of age, right? So which is quite easy to understand. And then y-axis is the so-called the disk fraction. And then this means that so if you look at the star-forming region, there are so many young stars, and then each young star may have a disk or maybe not. So then if the disk fraction is unity, so this means that all the young star has a protoplanetary disk. And then if the disk fraction is 0.5, this means that half of the star has a disk, and then half of them don't. So that's why by counting the number of the disk, number of the stars which have the disk, essentially we can kind of speculate how the presence of the disk evolve as a function of the cluster age. And then as you can see that if the cluster age is really low, then of course the most young star has a disk, right? So that's why disk fraction is high. But then if you look at the cluster, the older clusters, then disk fraction is decreased. So this means that maybe that many young stars don't have the disk anymore because maybe this guy is gone to the planet or evaporate or etc. So that's why by looking at this kind of statistical trend, we can determine that the kind of the age of the disk roughly. And then based on this one, we know that the typical the age of the protoplanetary disk is about 10 million years. So then and then actually it's interesting that depending on the location, the disk age might be different. Okay, anyway, so then this is nice, but then I think that I think it's much more interesting, right? If we can really watch how to form the planet formation in actions. And then so that's why the telescope called OMA comes into play. And then the OMA is essentially located in the Chile, and then we have lots of nice radio antenna there. And then actually before the OMAs, so this is the one of the young stars called HL Tau. And then before the OMA, we can see just one blob, which is nice because again the protoplanetary disk is there. But then we don't see any structures. And then after the OMAs, so then now we can see the gap like this. And then it's really impressive, right? I think this is exactly the same target. And then of course the observation is different because the observation is done by the older telescope. And then if you use the OMA, we can clearly see the gap. And then maybe the presence of the gap could be explained by the presence of the planet. And then the main reason is such a difference is that the spatial resolution, right? So then if you know the optics, spatial resolution is essentially determined by the wavelengths divided by the diameter of the mirrors. And then, of course, we couldn't make a huge mirror, so that's why for this case we try to combine the lots of the antenna to mimicking the one of the big mirrors. And then for the image before the OMA, which is taken by the Kalmans, and then that's the kind of the size of the diameter is about 2 kilometers. And then after the OMA, essentially diameter is increased by a factor of 8. So that's why now we can resolve the dark kind of structures. So that's why, and then again, still we don't know what's the origin of the gap, but then it's so exciting. Maybe that one leading hypothesis is that if you put a planet, then we can open up a dark kind of gap. So that's why we are so excited that we can now really watching the planet formation in actions. Okay, so then actually that OMA did some kind of surveys, and then this is kind of gallery of the structure of the disk. And then as you can see, we can see so many gaps, but then also that we can see another structures as well. So that's the protoplanetary disk has so many structures, and then still we don't know what kind of the structure is really, directly related to the planet formations, but then we can see that this kind of structure probably affect on that planet formation processes.
What is that? Sorry. What is the red dot next to the HTU lab?
Oh yeah, this one.
Yes.
I don't know. Yeah, that's a good point. I didn't check carefully, but I don't know. Could be the binaries, I guess, or I don't know, maybe planet or planetary disk. I'm not sure. But it's a good point. Yeah. Right. Yeah. I think that essentially the color is also represent the density. So that's maybe the high density object is really located there, and maybe truncate the disk.
Thank you.
Alright, so then our fundamental question. So then if you more care about just chip on the fission chip, so we already know some kind of answers. But then now we discuss a little bit about planet formation stuff, right? So then so now I put just Yami here, and then where do planet form? So actually again essentially the protoplanetary disk is the birthplace. And then if you like to know the forming environment, we should observe modeling the protoplanetary disks like this. And then so based on the disk fraction measurement, essentially we know that the disk lifetime of the protoplanetary disk is about 10 million years. So that's why if you like to form the planet, that's the kind of upper limit. And then so how? So actually I'm going to touch on later, but then still we don't know how to form the planet in detail. So that's why I guess we need we need your help, right? Especially the younger kids. So and then it's really important to run your imagination to propose new ideas. And then this is really the open field, and then anyone I think really can contribute. And then I try to touch on some of the basic ideas, but then if you guys have much better idea, just let me know, and then we're gonna work on together and write up the papers. Right? So, okay, so then let's try to go through the Yami planet. So maybe you guys already seen, but then this is a kind of the distribution of the planet. So then the y-axis is that represent the mass of the planet, and then the y-axis, x-axis is the orbital distance, and then there are so many dots, and then the different color represent the different the detection method, and then the solar system is down, that's shown by the black dot, and then clearly you see that the distribution of the solar system is quite different from the exoplanets, right? So then, and then there are some open space, but then this is more like an observational bias, and then this is a kind of new discovery space, and then currently we like to fill out this kind of space. And then so this is so this is more like a kind of scientific way, or I would say more boring way to show that this picture. And then maybe more fun way to see that is that so then this is actually the cartoon of the multi-exoplanetary system. And then central one is the solar system, and then the largest orbit is the Mars one. And then this is the Jupiter, and then this is the Saturn. And then essentially size corresponding to the size of the planet, and then color represents the temperature of the planet. And then it's interesting that the planetary system is so diverse, right? And then and then also this is again observational bias, but then we could detect that the planet really close to the center of the stars, and which is quite different from the solar system. And then now the yeah, and then and then some of them might be close to the solar system, but then it's the parameter space is huge. So that's of course we know the solar system quite well, but then it does not necessarily mean that the solar system is really common, right? And quite different. Okay, so then I think that sometimes it's again this kind of movie is good, but then if you like to characterize the planetary system, this is kind of convenient for the scientists to understand how it's going on. So that's why I'm going to coming back to this one. And then based on this diagram, actually, we maybe one things we can do is that how the distribution of the observed exoplanet system could be compared with the OMA image, right? And then as I said, this is more like that we are observing the planet forming locations. But then so then if the planet is really forming, say, one of the gap, then maybe we can speculate that the planet should be distributed here. But then as you can see, great. Yeah, and then as you can see, location of the gap is really away from central star, which is 50 AU. And then this is kind of corresponding to the red regime there. And then we couldn't observe so many planets there. So this means that maybe not all the gap couldn't form the planet. So maybe other mechanism is really important to explain the origin of the gap. But maybe some of them form there and then stay there. So then maybe we can observe the planet there. But then not all the planet not all the gap is really directly related to the planet formations. Okay, so then there are so many closing planets, right? And then if you look at the Mercury's, you look at the region within the Mercury, actually solar system is so empty. But then if you look at the exoplanetary system, there are tons of the planets there. And then we think that probably the planet forming material or formed planet should move within a protoplanetary disk. And then one of the ideas is the so-called migrations. And then
this animation shows the perturbation to the disk surface density created by an embedded 10 Earth mass planet. The main features are spiral density waves that propagate towards the inner and outer edges of the disk. These high density features exert gravitational torques on the planet. The outer spiral wave acts to pull the planet back against the direction of its orbital motion and therefore exerts a negative torque. The inner spiral wave exerts a positive torque. It's the outer spiral wave that normally wins, resulting in an overall negative torque that causes the planet to migrate inward.
Yeah, and then the movie says, essentially, if you put a planet in a gas disk, essentially the gravitational interaction happening between the disk and the planet, and then excite a so-called density wave, so which is more like same as a swing. So then if the orbit of the planet is corresponding to the orbit of the gas, then essentially the resonant interaction excite on some waves, and then you can see this kind of spiral wave, and then this spiral wave essentially transports a so-called angular momentum, and then planet is moving in the disk. So that's why this is one of the maybe the critical things to understand how the planet is distributed. And then also that these days another idea is proposed, but then still we don't know what's the efficiency of these ones and why say this kind of migration didn't happen to the solar system, but then why that process happened to the exoplanetary system, right? So this is just kind of big mystery right now in the planet formation theories. And then another thing is that if you look at the kind of red part, and then actually this planet is really interesting because Mars is larger than the Earth, right? But then also Mars is lower than the Neptune. So that's why this planet is called so-called super Earth or sub-Neptunes. and then there is no analog in the solar system. So that's why really important to characterize them first. And then this is one of the results done by the California team. And then what they found is that if you try to measure the radius of these planets, actually they are bimodal. So then one is that one peak is this showing a pink, and then the other peak is in the blues. And then there are gap between them. So then this kind of the bimodal structure is kind of useful for us to understand how to form the planet. And then based on some statistical analysis, this red one is more like composition is more like rocky. So then maybe that really the super kind of massive Earth. But then the beyond the blue ones, then the composition is more like gaseous or volatile rich. So this is again another hint of how to form the planets. Okay, so then now we just look at the radius distribution, right? So then if you know the radius and the mass, essentially we can compute the bulk composition. And then this the plot is really busy, but then the x-axis is the mass, and then y-axis is the radius, and then basically these lines corresponding to the composition of the planet. So then if the planet is made of purely the ions, then planet should line up these lines. And then Earth-like rock, which is essentially the 30% of the ions, and then 70% of silicate, all the planet is distributed here. And then again the kind of the super-Earth, which is more like the Earth-like rock. We don't know why, but then the composition is really like Earth-like rock. And then if you look at the sub-Neptunes, and then it's interesting that that contains lots of the volatile, maybe 50% of the waters. And then actually we don't believe that the planet is composed of the 100% of waters. But then might be a coincidence, but then that some planets really line up this line. So that's why these guys should contain lots of the volatile. So this means that again, maybe coming back to the migration, then planets maybe form the outer part of the disk and then gain the lots of the volatile and then migrate to a central star. So that's why these planets contain lots of the volatile. Okay, so then of course and then this is more like a bulk composition type of the things. But then we can also observe the atmosphere of exoplanets, and then we can put a concern of climate or habitability, and then this is one of the famous target, K2-18 beings, and this is one of the kind of the promising promising planet, which really like a habitable planets. And then now we can see the lots of the features, and then essentially this feature is really corresponding to the abundance or emission of the molecules. So by looking at some kind of some bump or depth, we can characterize what kind of molecule exists in the exoplanetary system. So that's why that right now we are more we like to do more observations of many targets using this kind of exercise, and then what kind of the kind of statistical trend will be, or something like that. So then so what's the next step? So then essentially again the OMA is really great, and then we can observe the lots of the gap. But then the main issue is that the gap is distributed much farther away from the central stars, right? And then actually what we like to do as the next is that we like to look at observe the closing regions, and then how that say terrestrial planet is formed, etc. And then and again here is empty space, but then that empty space is again because of the observational bias. Actually, we don't have a capability to observe the planet in a white space. So that's why we like to increase the target. So then, so that's why people are trying to work hard to how we can observe the planet in an empty space. Okay, so then that again, as I said, that now we can characterize the exoplanet atmosphere. So then that definitely we like to do more observation, and then depending on maybe planet mass or depending on the location of the planet, maybe that kind of structure might be different, and then this is really useful to understand the planet formation. So that's why essentially our field is really heading towards the discover or characterize Earth-like habitable planets. and then also we like to characterize the forming environment as well. So then by looking at the formed planet or mature planet, and then we can get the kind of end product. And then if you look at the forming the environment, then of course we know that the kind of initial conditions, right? And then actually we know that we are pretty sure about it, that the main reason is that of course if you don't, of course it's really tricky to predict the future, but then to do that I think it's really good idea to ask the ChatGPT and then what the future look like. And then this is a kind of my experiment, and then so what is the key science topic in the exoplanet in the next decade, and then say visualize it, and then so here is the outcome, and then of course the ChatGPT also support the habitability of the planet, right? And I don't know why, but the top part is cut, which is a really sad part, but then essentially ChatGPT also understand what's the future look like. So and then and then another that the backup is that NASA is also really interested in the observing the habitable world. And then as Mayuko mentions, that essentially the NASA, one of the biggest goal in NASA is that we like to observe the habitable planet. And then the next flagship mission is the so-called Habitable World Observatories. And then here is a kind of nice kind of short movies where
the stars above.
Explain the HWO.
What secrets do they keep? One of our biggest questions has always been, are we alone? We've now discovered thousands of planets beyond our solar system, but how many of those distant worlds have the conditions for life as we know it? How many have water vapor, a beacon indicating that oceans might be present? How many have gases like oxygen and methane, possible signs of life itself? And of those, which might truly have life? After decades of asking, a future NASA telescope could bring us the answers. The Habitable World Observatory is a future mission designed in the tradition of the Hubble and Webb space telescopes. It will use its unique and sensitive eyes to see planets like our own, hiding in the light of their distant stars. Astronomers could then point this mighty space observatory to the most promising planets, those that may hold liquid water. With the help of its coronagraph instrument, which blocks out the dazzling starlight, the telescope will look for undiscovered Earth-sized planets in the star's habitable zone where liquid water could exist. The light from each planet will be split into a vibrant spectrum of colors, revealing clues to the chemical signatures we seek. From there, we can attempt to discover if a planet's atmosphere contains water. And from there, other signals like oxygen or methane. Should all these signs align, the Habitable Worlds Observatory would delve deeper to reveal other hidden clues of life. With further study, we could find signs of sprawling oceans and rugged continents. And if signs of life are revealed, keep a watchful eye for changes over time. This magnificent observatory could discover dozens of worlds akin to our own in its first 5 years. The telescope will gather data on a wide variety of worlds, placing our own solar system in the context within the grand tapestry of existence. And the Habitable Worlds Observatory will, like the other Greek cosmic watchers, Hubble, Chandra, Spitzer, Webb, and soon Roman, also conduct a wide range of revolutionary observations of our cosmos, improving our understanding of how our universe led to potentially habitable worlds. Thus, the Habitable Worlds Observatory will help us embark on a quest as grand as any, to tell the story of life in the cosmos, and whether or not we are alone.
Okay, yeah. So then that now we like to launch the Habitable World Observatory 2020-40s, and then to do the actually that the people at NASA or JPL or any other the NASA research center, and also including the universities, and then actually in the world, especially JAXA people are really working hard to launch this kind of telescopes, and then particularly that I think that this is it's going to be your telescope, right? So that's what you need to use in the future. So then, yeah, I think that that's it. And then thank you so much for your attention. So now I'm happy to answer any question you have.
Thank you so much. Do you have any questions?
Yes, actually, I have one question that is about the observation bias.
Mm-hmm.
Especially the relationship to time.
Time.
Yes, observation time.
Mm-hmm.
Actually. Because right now we are trying to work our way to determine what is to have statistical analysis on what is an average, I would say, exoplanetary system out there.
Mm-hmm.
Or to try to determine exoplanet formation and so on. But we have huge gaps in our
Yeah, that's a really
sample
good question.
of,
Yeah.
data, because there are huge biases. And one of the question I have is this something we have a chance in our lifetime to somehow deal with, or are we about to have the same kind of problems as the people who determined the heliocentric system had in the few centuries ago, which is that we will need centuries of observation to be able, once again, to have a more statistical, I would say, complete data set?
I say, yeah, I think that's a really good question. And then of course that the region we can observe in the sky is really limited, right? And then we couldn't get a complete the sensors of the exoplanet, unfortunately. But then so that's why what we like to do is that so this is a kind of mature planet, right? And then and then still I think it's really biased. And then the one things we can do is that maybe we can look at a different area, and then how this the approach is similar or different. That's a kind of one way to address. This is really the kind of more complete picture of the sensors of the exoplanet. And then another thing is that maybe we can look at the younger age of the system, and then maybe this kind of distributions change with time as well. So then of course we couldn't observe all the planet in the sky, unfortunately. But that what we can do is that essentially we are looking at again different kind of stars, the area or skies, and then try to make sure that how this kind of picture is similar or different. That's another kind of key information of the planet formation.
Actually, my question was a little bit more about the time for planet rotation, because, for example, of course there is the area aspect of the issue, which you addressed, but there is also, for example, the fact that we have nothing into the 10 to 100, almost no observation in the 10 to 100 AU area, even though plenty of exoplanets exist. And then how can we manage the problem then to do an orbit of the
I see.
will you need X years and then
Right. Yeah, I see what you mean. Yeah, essentially, to confirm the detection of the planet, actually, we like to, detect. I think that detect the multiple orbits. So then you are right. I mean, if the distance from central stars increase, then we need more time. And then for one of the methods, so-called the radial velocities, as a Doppler method, then actually the first discovery was done in 1995, right? And then now we have about 30 decades. So that's why maybe we can reach to about 5 the AU-ish about the location of the Jupiter. So that's why maybe around this regime getting complete. But then yeah, you are right. If you like to observe this area or method, then we need more time. And then, but actually, it's interesting that if you look at a different method, so for example, the micro lensing, then some method is sensitive to the different parameter space. So that's why we don't have to wait to such a long time.
Okay.
So that's why we like to use the multiple method to cover this area. So then that's a really good point. Yeah.
So we can avoid the
Yeah.
100 years.
Right. You don't need to
time
ask your
necessary
grandsons
of,
or grandson
confirmation.
to confirm. Yeah, exactly. Yeah.
Okay.
Okay, any other question?
Okay.
Yep.
That's good. Sort of extending on from that point, if I understand correctly, the gaps in the protoplanetary disks,
Right.
if you can establish that they are planets, then you can have more data on
Yeah. Right. Exactly.
planets and distances.
Exactly.
And
Yeah.
is that potentially another method that can be plot on that?
Exactly. Yeah, that's again another really the good point. So that's why the coming back to these figures, and then we couldn't wait for a really long time to to see the planet, right? So that's why to fill out this parameter space, actually we are gonna use the so-called imaging method, and this is more like just almost like taking a pictures, and then once we take a pictures, and then wait a little bit, and then we can really see the motion of the planet. Then that we can confirm this planet is bound to the system, or maybe the background object. So that's then maybe we don't need to wait a really long time. Maybe a few years might be good enough to see that that kind of the light source is really bound to the system or not. And then depending on the brightness, we can confirm this is more like a planet or stars or maybe background object. So.
Thank you. Any other questions? Yes.
This is more of a hypothetical question, but if we somehow manage to find like a planet that's similar to Earth, like say tomorrow, with multiple biosignatures, what will be the next step? Like, if it's very close to Earth, like only like a few light years, will we try to send probes, or will we send like I don't know, like radio signals? What will be the next step if we actually find like a second Earth?
Yeah, I mean that's a really good question. So then currently that in the field, we just know that we are just excited to just observe the system, right? And then still we don't know what's the next step. But then the essentially there are so many things we can do, right? So essentially monitoring the system and then how say biosignature change with time or not. That's maybe one interesting question. And then also to say maybe to put a more tighter constraint on the say origin of the life, etc. Or maybe the origin of the planet itself is also another interesting question. And then right now, but then technologically actually it's really tough to observe such a system yet. So that's now kind of we define the goal to detect that planet fast. And then I think once we get once we get more observation about it, and then that the field have much better idea, it would be a nice next step. So, but then right now I think it's a really good point. I think that even the NASA, I think that we are thinking that just we like to discover, right? And then that's of course nice goal. But then for the scientists, of course, we like to know the origins or the mechanism so why we are here, right? So that's a kind of ultimate goal. So that's one. But then detecting one planet is probably not good enough. So then we like to get maybe handful or a 10-ish object will be needed to get a better understanding of the origins or evolutions or process and operating in the system. So.
Any other question? Oh, yeah.
Yeah, thank you.
It's challenging a bit when you say why we are here. For me, this is a more philosophical question, kind of this natural science question. So I don't know if you can answer with knowing about what happened in the beginning, but would it answer personally for you the question why you are here? Not here, but.
Yeah, I mean that's a really deep question, right? So yeah, right. So then I think that I don't know. I don't have a simple answer. And then of course, as you said, it's more like a philosophical question. And then we can define that question in many ways. But then maybe that the one things we are really excited about is that we can now try to address the things scientifically, not philosophically. So that's and then that for me, I don't know the personally it's I don't know. It's a good question. So but then that hopefully that human being, each people has some kind of your own meaning, right? To give a birth, and then maybe you like to achieve something on your way, and then so I don't know. It's hopefully that the in the next like the kids like this, they can eventually merge to because a long time ago that kind of question is coming from the philosophies, right? And then evolve into the more scientific thing, right? The Galileo, these guys did, and then now it's separated, but then now we try to merge to the single point, and then actually I don't have a strong religious thoughts about it, but then maybe that we can know that there might be God there and created, or maybe matrix might be we are living in a battery's life or something like that. So we're gonna find out future soon. So
Any other questions? Actually, I have one question.
yeah, of course.
So yeah, as you are a member of the Habitable World Observatory.
Yeah,
science
right.
team. So like, what it is like to be a member of those science team of very future mission. So what is the current status and what are you like talking about in the discussion of?
Oh yeah, right now actually no, that this is more like a really the technical things, and then it's really nice questions. And then actually I show the movies, but sorry that right now that we are making the future telescope. I mean that there are so many things we need to do. And then that right now that especially this kind of telescope, we need to define so-called the kind of key science questions. And then depending on the science question, we define some kind of instrument which is needed to address the questions. And then right now we essentially select some kind of key science questions. And then how that kind of science question will be addressed by each telescope, each instrument and telescope, the architectures of these things. And then right now we already established, select some of the science cases for each instrument, and then particularly the Habitable World Observatory, we already decide to, mount the four telescope. One is the so-called coronagraph, and then this is more related to the detection of the habitable planet, and then the other one is that the imagers, and then that maybe imagers the imager maybe really I forgot the detail, but then the imager also related to some kind of science cases, and then critical for the galaxy formation, etc. So then now we know that again. We try to select some kind of science cases and then define the specification of the instrument more carefully. So, but then still that kind of effort is just started, and then there are so many ways to jump into the effort, and then right now that's so-called thesis, science, community science instrument technology team or something is formulated. So then, and then that especially for the international collaboration, JAXA or Japan or ESA or Europe people try to jump in and then define that telescope capability more tightly. So yeah, but then again, our idea is try to launch in 2040. So that's there are still a long way to go, and then that. Maybe that science cases evolve with time, and then maybe we need to adjust some capability, etc. And then maybe another interesting point of the HWO is that we try to be serviceable, like HST. So that's why essentially HWO try to launch in a L2 point. So that's why essentially orbiting around the suns. But then that in the future we like to send a spacecraft to and then land it on the HWO and then changing the instrument for the future. The future observation. So that's why there are tons of the opportunity available. And then actually reach out to that industry community as well to make how we can create this kind of telescope efficiently or cost effectively. So that there are so many. I think there are so many opportunities right now.
Thank you. So
Sorry, L2, how far out is that?
I think it's almost like opposite side of the Earth, I think. But then it's not so. The water, yeah, actually.
Like further than the moon, right?
Yeah, of course, yeah, it's much farther. And then that habitable, that Hubble Space Telescope, it's really low orbit, and then the L2 is much far. But then it seems that technologically it's possible to do that. Yeah, so that's why it's gonna be really the super, our idea is that this is more like a super Hubble, and then and then based on the HST exercise, the serviceability is really amazing to keep updating the telescope, and then so that's why we like to include it. But then of course it's really depending on the funding or cost, etc. So still details the TBDs. But we are kind of dreaming about this kind of telescope.
Okay.
Yeah.
Yes.
Of course, yeah, please.
Thank you very much for your amazing talk. I have a two-part question, and the first part is when you mentioned that Habitable World Observatory is going to be launched in 2040.
Yeah.
Around 2040, and why is it around 2040? Is it because of the launch slot is not there yet? Is it because of you're waiting for tech maturity? Are you waiting for a specific orbit, transfer orbit, or something? What's the reason for that? And
Yeah, I mean that's a really good point. I mean if you launch a spacecraft to the solar system and then investigate those things, there are some kind of time window, right? So then sometimes if you send a spacecraft to say Jupiter or Neptune, then we like to use the gravity assist and then accelerate. So that's why there are time window. But then for the Astro mission, essentially there is no time window. And then main reason why we say 2040 is that mainly that the two things. One is that of course the technology things. Maybe we still need to develop some of the instrument to achieve the science goals, and then we are expecting that maybe about 5 to 10 years will be needed to achieve the science goal using some technologies. And another one is of course the funding. So that's the actually next one is that the Roman Space Telescope. Then that will be launched about 1 or 2 years, and then this is the next one. So that's why we need to wait about 10 years each to complete the everything and send it. So.
thank you very much for the very comprehensive question. And that goes to my second part of the question. Even though I work at a space agency, I don't know why a lot of space science missions, they always take so long in the future. Because if you plan for shorter mission, you can always plan for shorter mission with the rockets, right? You can always plan, okay, we're gonna launch something in the next 2 years, 3 years, right?
Yeah.
With H2 rocket or H3 rocket.
Yeah.
But why science mission generally takes so long in the future?
Yeah, I mean that's
Do you have any idea or?
Right, I think that's another also excellent question. And then especially that I would say right now kind of two modes, right? So one is that as you mentioned, we like to launch the technology so quickly, and then maybe SpaceX or some kind of the private sector like to adopt that process, and then always because now that say iPhones or this technology is so great, so that's why don't you use that technology to launch it? But then but for NASA, that's a kind of the new I think stream or paradigm. But then for NASA, more like a government size, they are so conservative. And then actually we are kind of the ranking system, so-called the technology readiness levels, and then the so-called TRL. And then if you like to attach that kind of technology to launch in a space through the NASA channel, we need to achieve certain level. And then the one of the characteristic time scale is that once the technology is available on the surface of the Earth and they use it for 10 years, NASA is so happy to use it for the space. So that's all the technology we ship into the space is actually at least 10 years older than the technology right now. So that's that because of course the space is so harsh environment, right? So we like to make sure that everything's working perfectly and everything's work correctly, and then we need to test so many things. So that's why we need about 10 years to make sure that all the technology is right. But then NASA also recognize that this is so conservative, and then so that's why NASA is now kind of creating the small mission, so-called the CubeSat. And then if you use the CubeSat, which is really more like just the box size, and then they are more happy to use the really advanced technologies. But then just that because we are using taxpayer money, and then that mission is almost close to $1 billion US dollars, or maybe close to $10 billion, and then they never like to fail, right? So that's why we really like to need a really long time to make sure everything's working correctly. But then I think that because of SpaceX or the other space agents, the space companies, I think the situation is really changing, and then maybe that now we can use the more advanced technology so quickly, I guess. And then I think the random scale of the space, the engineering is changing so rapidly these days.
Thank you.
Thank you very much.
Okay, so if you have further questions, he will be around for a while. So, yeah, directly.
Yeah, please feel free to stop by and say hi to me. So I'm happy to have a chat more.
Okay, so thank you again for Hasegawa.